So time is not the only thing that changes with varying speeds. In fact, all of space around you consists of a fabric that we can represent with a grid called space-time. And this space-time, which represents all the space around you, shifts in shape at varying speeds. And it's this shift that causes variations or relative changes in the quantities we're used to, such as time. Another one of these quantities is length. So it turns out that the length of a moving object relative to some observer is equal to its length when it's stationary, multiplied by the square root that we saw earlier. So 1 minus v squared over c squared. And what this means is that if we have an object moving at some velocity relative to an observer, it appears to be a fraction of its original length. In other words, if you're moving at some velocity, you appear to get shorter or you contract, and this is what we call length contraction. Another thing that you can notice is that if you're moving at the speed of light, so if your velocity is equal to c, then 1 minus c squared over c squared is equal to 0, and so your length is equal to 0. So anything moving at the speed of light, such as light itself, or the photons that compose light, they have lengths of 0. And that's one of the reasons why anything else other than light cannot move at the speed of light or at a greater speed. So this effect is always present. It's present in your regular day life. So if someone's moving in a car, moves past you, they're actually shorter than if they were stationary right beside you. But you can't notice this change since the speed that the car is moving at is insignificant compared to the speed of light. However, suppose we have an observer that is not moving, and there's a rod in front of them which they measure to be 1 meter in length when it's stationary. And then let's say this rod moves at some speed close to the speed of light. Then this observer might say that the rod is 1.7 meters, 0.7 meters. And so it appears that the rod has shrunk in size. And the key here is that it's not that it appeared to shrink, it actually is shorter. So from the point of view of the stationary observer, the rod did indeed shrink. It actually became shorter. However, from the point of view of someone moving along with the rod, or the rod itself, it would not feel this contraction. So it's very similar to the idea of time dilation, where a person moving within a rocket ship, moving at a very high speed, would not feel that their time is moving slower. However, from the outside looking in, we know that their time is indeed slower. So mass also changes at varying speeds, which we call relativistic mass. So this relativistic mass, or m, is equal to your stationary mass, or m naught, divided by the same square root we saw earlier. So 1 minus v squared over c squared. And we can see that if something is moving at some speed relative to an observer, it's going to appear to have a greater mass. And it's actually very important to stress, it's not that it appears to have a greater mass. Once again, it actually does have a greater mass relative to that observer. It's also always true, but the speeds that we see in everyday life are not significant compared to light, so you don't really notice this change. Another thing that we can conclude is that objects moving at the speed of light will have a mass, or a relative mass, of infinity. Because 1 minus c squared over c squared is 1 minus 1 or 0, so you're dividing a number by 0, you're going to get infinity. Now, what this means is that any quantity that depends on mass also changes at varying speeds. So one of those quantities is momentum. So if we look at the classical equation for momentum, or momentum according to Newton, it's equal to the mass times the velocity. Now, knowing what we know about masses and relativity, we can create an equation for the relativistic momentum. It's going to equal your stationary mass divided by 1 minus v squared over c squared, all under the square root, multiplied by your velocity. So momentum changes at varying speeds compared to different observers. And once again, if you're moving at the speed of light, we're going to be dividing by 0, and so your momentum is going to equal infinity. And once again, both of these conclusions do not make any real physical sense. They betray or they disobey the laws of physics that we had previously, such as conservation of energy. And so, nothing except light can move at or faster than the speed of light, or c. So another quantity that depends on mass is kinetic energy. Before we get to that, Einstein discovered that any object that has mass also has an intrinsic energy, which he called your rest energy. And this is equal to his famous equation, mc squared, or more specifically, your stationary mass relative to an observer times the speed of light squared. And this quantity, like almost all others, changes with varying speeds. So your total energy is equal to your rest energy, or mc squared, divided by the square root of 1 minus v squared over c squared. And this total energy is equal to your rest energy plus your kinetic energy. So you can see that if you're moving at some speed, your total energy is going to increase since you're dividing by a number less than 1, and that increase is equal to your kinetic energy. And so our relative or our relativistic kinetic energy is equal to your total energy, mc squared, divided by the square root of 1 minus v squared divided by c squared minus your rest energy, since we'll take that to the other side. So simply mc squared. So that is equal to your kinetic energy. And it might look different than your classical equation. So Ek classical, according to Newton, is equal to 1/2 mv squared. But if you use some math tools that are outside the scope of this course, you can see that this equation at low speeds equals the classical equation. And to show this, we'll suppose that we have an object that has a rest energy. So there's an example. We'll suppose that we have an object that has a rest energy of 100 kilograms and which is moving at a velocity of 0.1, the speed of light. So at this speed, both equations should agree there should not be a much noticeable change. It's when you get to around 0.5 or half the speed of light where you're going to notice a change. So if we analyze the situation and find the kinetic energy according to the classical equations, we'll find that it's equal to 1/2 times 100 kilograms multiplied by the speed squared, so 0.1 times c squared, and this is equal to 1/2. 0.1 is simply 1/10 squared times 100 kilograms times the speed of light squared, and this is equal to, if you plug it into your calculator, 4.5 times 10 to the 16 joules. If we do the same using our relativistic equation, it's going to equal, we'll factor out our mass times the speed of light squared. What we're left with is 1 over the square root of 1 minus v squared over c squared minus 1. Then we can substitute in, we get 100 kilograms multiplied by the speed of light squared, 1 over 0.1 c all squared divided by c squared. The two c squareds are going to cancel out, so we get 1 minus 0.1 squared minus 1. And if you plug that into your calculator, you'll get 4.53 times 10 to the 16 joules. So you can see that they're pretty close in terms of percent difference. The actual difference is a large number, but in terms of the percent relative to their magnitudes, it's pretty small. And so the relativistic equation simply reduces down to the classical equation at relatively low speeds. Now it's important to note that the relativistic equation is always right. So the actual kinetic energy is indeed 4.53 times 10 to the 6 joules. However, the classical equation provides a reasonably accurate approximation at low speeds. So now we have a couple of questions for practice. So for the first one, the kinetic energy of a particle is equal to its rest energy, and we want to find the speed of the particle in order for this to be true. So for these questions, you're going to have to use the relativistic equations. If it turns out that you don't need them, you'll still get the correct answer. If it turns out that you do need them, if you use the classical equations, you're going to get the wrong answer. So you have to use the new equations. So we know that the rest energy is equal to the stationary mass multiplied by c squared, and the kinetic energy, according to relativity, is equal to stationary mass c squared divided by the square root of 1 minus v squared over c squared minus mc squared. And we know that they're equal. So we're going to set these two equations equal to each other and then isolate for v. So we have that mc squared is equal to mc squared divided by our square root minus mc squared. So if we bring this mc squared to the other side, we'll get 2 mc squared is equal to mc squared divided by the square root. And now mc squared is common on both sides of our equation, so we can simply factor it out or divide by mc squared. So these two terms are going to cancel. And then we'll multiply this square root to the other side and divide by 2. So we'll get that the square root of 1 minus v squared over c squared is equal to 1/2. Then we'll square both sides. So 1 minus v squared over c squared, to get rid of the square root, is equal to 1/4. And then we'll isolate for the fraction that contains the velocity. So 1 minus 1/4 is equal to v squared over c squared. 1 minus 1/4 is 3/4, and we'll multiply by c squared. So 3/4 c squared is equal to v squared, and of course we want to find the speed of the particle, so we'll square root both sides. We find that the speed is equal to the square root of 3 divided by the square root of 4, which is 2, times the square root of c squared, which is simply c. Therefore, in order for a particle to have its rest energy equal to its kinetic energy, it has to be moving at the square root of 3 over 2 speed of light. For our next question, we have an electron with a speed of 0.99 the speed of light, which has a momentum equal to a ship of 4.38 times 10 to the 7 kilograms moving at some speed v. We want to find this speed. So we know that the electron is going to have a momentum according to relativity. So the momentum of the electron is equal to the mass of the electron when stationary times its velocity divided by the square root of 1 minus its velocity squared over c squared. And this is equal to, we won't suspect that a ship is moving at a very high speed, so relativity doesn't really apply in the case of the ship. So we're simply going to use classical momentum here, which is simply mass times velocity. So the mass of the ship, or ms, times its speed vs. And now we're going to want to isolate for Vs. So it's quite simple. We only have to divide by the mass of the ship. So Vs is equal to MO, or the mass of the electron when stationary, times the velocity of the electron, divided by the mass of the ship times the square root of 1 minus v squared for the electron divided by c squared. And if we plug in what we know, the mass of the electron is a 9.1 times 10 to the negative 31 kilograms. The velocity of the electron is 0.99 c. The mass of the ship is 4.38 times 10 to the 7 kilograms. And our square root is going to be the square root of 1 minus, since the electron is moving at 0.99 c, we're going to have 0.99 squared, c squared, divided by c squared, so the two c squareds are going to cancel out, so all we're left with is 0.99 squared. And it turns out, if you plug this into your calculator, where c over here is 3 times 10 to the 8 meters per second, your velocity for the ship is going to equal 4.37 times 10 to the negative 29 meters per second. In other words, the ship is barely moving. And we can see that these 2 kilograms are going to cancel out, and all that we're left with is the units of meters per second. So we do indeed get a velocity as our final answer. Now for our last question, we have two rockets of rest length L0 that are approaching each other at 2/5 the speed of light. We're going to assume that the rules of relative velocities remain the same at this speed. So in that case, what does each ship measure the length of the other to be? So we have two ships. Ship number 1 is approaching ship number 2, and ship number 2 is approaching ship number 1, so they're moving towards each other. Each of them is moving at a velocity v, and v is equal to 2/5 the speed of light. So for this question, we want to know what each ship measures the length of the other to be. The question is symmetric in the case where if we look at one ship, or we consider the view of one ship, it's going to be identical to the view of the second ship, since they're both approaching each other with equal velocities. So we only have to solve it once. If we consider the point of view of ship 1, it's going to see ship 2 moving at a relative velocity of, it's approaching at 2/5 the speed of light, and it's moving towards it at 2/5 speed of light. So we simply add the velocities to find the relative velocity, as you saw in a previous chapter, and this equals 4/5 the speed of light. Now we can use our equation for the relativistic length. So the length of a moving object relative to an observer is equal to its stationary or rest length multiplied by the square root of 1 minus v squared over c squared. So in this case, we're not given L0, so we're simply going to find an equation in terms of L0. So the moving length is going to equal the rest length multiplied by 1 minus, our velocity in this case is 4/5 the speed of light, squared divided by c squared. And so the two c squareds are going to cancel out. We're left with 1 minus 4/5 squared. 4 squared is 16, 5 squared is 25. So we get 1 minus 16/25. What we're left with is 4 plus 5, or 9/25. And the square root of 9/25 is 3/5. So the length of the other ship relative to the one we're considering is going to be 3/5 its original length. In other words, from the point of view of the first ship, the second ship, 2 over here, is going to appear to be 3/5 its original length. At the same time, from the point of view of the second ship, the first ship is going to appear to be 3/5 its original length. From the point of view of the ships themselves, they're not going to feel this contraction, and in all cases, each one is going to be correct, because Einstein said that every single inertial frame of reference, which these are since they're moving at constant velocities, every single one is equally valid.